But okay, before we get into the review of quantum mechanics, let's very quickly look at what we did in lecture number 11. So lecture number 11, we mostly concentrated on coherent mode representation of a field. In this representation, essentially a partially coherent field is written in terms of or represented in terms of fully coherent fields. So for example, we looked at coherent mode representation in the finite dimensional basis of polarization. A general polarization density matrix, a general polarization matrix can be represented like this. This is in the xy basis. Now one can always find a basis x prime y prime in which this polarization matrix is diagonal. So this essentially means that a general polarization matrix can be represented as a sum of two different polarization matrices, each of which is actually completely polarized. For example, this 1 0 0 0, this represents the polarization field that is polarized in the x prime direction, and this represents the field that is polarized in the y prime direction. And so this field J can be represented as the incoherent mixture of a field polarized in x prime direction and a field polarized in y prime direction, and this A1, A2 are the proportion of the two polarizations in that mixture. Here we note that this is actually not the coherent superposition, this is basically an incoherent superposition. That means this is just a mixture of this and this. Similarly, one can have coherent mode representation in the infinite dimensional basis, and in this case the coherent mode representation can be written in general as like this. So this is the cross spectral density function of a partially coherent field. This can be written as a sum of the several cross spectral density function. Here we have a finite number of cross spectral density functions. So this W n rho 1 rho 2, this is the cross spectral density function corresponding to a fully coherent field, and that's why we are representing it as psi star n psi n, and there is no ensemble averaging here. So this W, which is partially polarized, can be written as a sum of this W which is partially coherent can be represented as a sum of cross spectral densities that are completely coherent. Again, this sum is an incoherent sum because alpha and ns these are a real number and not complex number. So that's an incoherent sum as opposed to coherent sum. In continuous basis, one can also have an infinite number of coherent modes in addition, instead of having just the finite number of modes, and in that case the W can then be written as an integral over such modes, where this W rho 1 rho 2, this is just a coherent mode. Okay, so now let's get to today's lecture. So here today we will just do a very quick review of quantum mechanics. Most of this should be familiar to everybody taking this course. So in quantum mechanics, the very first concept that we encountered is that of a state vector. Quantum state is always represented by a state vector. This is completely an abstract mathematical quantity. It's just like a black box. One can extract information from the state by operating with an operator and so on, but as it is, this state is just like an abstract mathematical quantity and is like a black box. Now a state can be represented as a superposition of other state vectors or some basis vectors. For example, state psi can be represented as some other states, psi 1 and psi 2, as a coherent sum, coherent superposition. A state can also be represented as a superposition of discrete basis vectors. For example, L is the orbital angular momentum basis, orbital angular momentum basis vector, and one can have a state that is a superposition of such basis vectors. One can also have a state that is superposition of continuous basis vectors. For example, here we have the momentum basis vector, and a state can be written as a superposition of this momentum basis vector. The next concept we encountered is that of a wave function. Now when this this state that we have is just an abstract quantity. Now when this state vector is projected onto some basis, then that projection, that is which is defined as the inner product, is called the wave function of the state in that basis. So for example, we have a state psi, and if we take its projection in this discrete basis L, orbital angular momentum, then what we obtain is just a complex number. So that CL is actually the projection of this state vector onto the orbital angular momentum basis. So that is just a complex number. But if we, instead of taking it over a discrete basis, if we take it over a continuous basis, for example like a position basis, then we have the state vector psi, we take its projection onto the position basis, and then what we obtain is just complex function. and this complex function is typically referred to as the wave function. So this is the wave function in the position basis. Wave function is always in a given basis. You can have, for example, here this is the wave function of the position basis vector itself. So if x and x prime are position basis vectors, then let's say x prime is position basis vector, so its projection in the position basis is just a Dirac delta function. Similarly, we can also have the same state psi being projected not in the position basis but in the momentum basis, and in that case what we have is the wave function in the momentum basis vector. So this is the concept of wave function, that is the state. If we take its projection onto some basis, then what we obtain is the wave function in that basis. If it's a discrete basis, we just obtain a complex number. If it's a continuous basis, we obtain a function which we call wave function. The other concept is that of a probability density. And this is basically the absolute square of the projection or the wave function. So the L psi, for example, this is the projection in the discrete basis. So CL is a projection in the discrete basis, and CL square is a probability in that discrete basis. This essentially means that this is the probability of this state psi being found in orbital angular momentum state L. So that's what this CL mod square is. If it's a continuous basis, then what we get as the projection square is the probability density. So for example, this x psi, which is psi x mod square, this is the probability density in the position basis. The psi x mod square dx, that is px dx, that is the probability that the system is between x and x plus dx. Of course, we can integrate it from some value to some other value to get the probability that the system is between the two given x values. So that is the concept of probability density. Next is the concept of operator. Now we have the state vector in quantum mechanics, which is just like a black box. If we want to obtain some information from that, we'll have to act on it with some operator. So for finding the value of a physical observable, one operates on the state vector using Hermitian operator, and of course for evolving the state, one just uses what's called the unitary operators. So Hermitian operators and unitary operators these are the two most common operators we encounter in basic quantum mechanics. And again, just like states, operators are represented using a basis. So for example, position operator in the position basis is represented just like x, but the momentum operator in the position basis is represented as minus IH bar del del x. Of course, we can have the momentum basis representation of position operator as well as momentum basis representation of the momentum operator. So every operator can be represented in several different bases. Next, we have the concept of eigenstate. This says that if a state is an eigenstate of some operator, then the corresponding operator does not change the state but yields a fixed value of the observable called the eigenvalue. So if we know that the state of the system is some eigenstate of some operator, then if we act with that operator, then for corresponding to that operation, we don't change the state. This is usually in quantum mechanics, whenever we operate a state with an operator, one actually changes the state. But if it's an eigenstate of a given operator, then for that operator the state doesn't change. So for example, we have this momentum eigenstate. Its position representation is given by e to the I p naught x by h bar. Why we call it a momentum eigenstate is because if we operate it with the momentum operator, we'll just get this p naught value out, and the state remains the same. So that's why this is a momentum eigenstate with the eigenvalue p naught. Similarly, we can have position eigengate x naught. We write its position basis wave function. It is given by this delta function delta x minus x naught. We call this as the position eigengate with the eigenvalue x naught, because if we acted with the position operator, this state remains the same, but we get the eigenvalue x naught. So that is the concept of the eigenstate. Then within quantum mechanics, we can represent the state in a given basis. We can again represent the state in some other basis. So by changing the basis, one can express a quantum state from one basis to another basis. For example, an x basis vector can be represented in terms of p basis vector, momentum basis vector, and that's how it is done. This is derived in most basic quantum text. So here this position basis vector is represented in terms of this momentum basis vector. Of course, when we can invert this and then represent the momentum basis vector in terms of the position basis vector. So this is just a change of basis and the change of representation. So it is just not the basis vector we can represent this manner. We can also have a basis transformation or change of basis between wave functions. For example, psi x, the momentum, the position wave function, can be represented as in terms of momentum wave function like this. In fact, here we just take inner product with psi on this side and that side, and that gives us the wave function. So here the position wave function is written in terms of the momentum wave function. Similarly, we can also write momentum wave function in terms of position wave function just by taking the inverse of this. So here you note that the psi x, the position basis wave function, and the momentum basis wave function, they actually form a Fourier transform pair. So both the psi x, psi of x and psi of p, these are two equivalent representations of the same state psi. In fact, this Fourier relation that we have between psi x and psi p, this is the basis of all spatial interference effects that we see. So for example, if let's say the position basis wave function is psi x is equal to 1 for minus a to a and is 0 otherwise. This is just a single slit situation, that here in x the wave function is just 1 in this region, otherwise it is 0. Now if we take the Fourier transform of the psi x, that means we find the if you want to find the psi p, we just take the Fourier transform of this, which is which can be shown to be this 2a sine ap by h bar divided by ap by h bar. This is what's called a sinc function, and this is given by, so psi of p is the Fourier transformation of the psi of x, or this is just the momentum basis representation, and this is the position basis representation of the same wave function. Now here this is the sinc function that we see quite often when we do the diffraction through a single slit. Another example, here is the position basis wave function that is in the form of a double slit. That means the psi x is 1 in this region and in this region, otherwise it is equal to 0. Now for such a wave function, if we want to find its momentum representation, we can show that this is just like a big envelope on this one filled with this interference fringes. Again, this is the typical interference pattern that we see in a Young's double slit interference. So here we have the position basis wave function, and the far field pattern that we get here is actually the momentum basis wave function. Yeah. Okay, so we can take this is not just the single slit or double slit. In fact, this thing works for a very generic field. In fact, we can have a two-dimensional version of it. And in the very first lecture, we had this example in which we showed that we can generate very complex pattern by this simple Fourier transformation. And all that is at work here is this Fourier transformation between psi x and psi p, and the fact that the position basis wave function and the momentum basis wave function, they are related by a Fourier transform. Okay, so next is the concept of measurement. This is quite an involved concept within quantum mechanics, and maybe we'll do a separate lecture on what is measurement in quantum mechanics. But for now, measurement is just an act of obtaining some information about the quantum system. So when we measure the state, for example, we have this quantum state, and we want to obtain its position information as to where the system is. Now this act of obtaining the position information through any measurement device, this is completely uncertain as to what value of the position that the measurement is actually going to give. So for example, if we try, here we have a quantum system, for example, photons coming from the source, it goes through this kind of system, and now we are looking at this screen as to where the photon hits. Now where the photon hits this screen is completely random, and it just simply cannot be predicted. So if we actually do the measurement, we find that sometimes it is at x1, sometimes at x2, sometimes at xn. In fact, this is a continuous range of values that we have. But exactly which x, exactly where the photon will land up on the screen is completely uncertain and cannot be predicted. So the measurement value, the outcome of the measurement simply cannot be predicted. And this is actually related to the concept of the wave function collapse, that an act of measurement collapses the system, and it collapses the system into one of its eigenstate x. So it is actually impossible, even in principle, to predict what the state the system will collapse into after the measurement. Of course, there is an exception, and that is when it's an eigenstate. But if the system is not in the eigenstate, then one can never ever predict as to what state the system will collapse into. One can only find out the probability that that an act of measurement, what is the probability that an act of measurement collapses the system into eigenstates between x prime and x prime plus dx prime. So that can be predicted, and which is given as this psi x prime whole square at dx prime. So that's the probability density, position probability density times the dx prime. That is the probability that the act of the measurement will collapse the system into eigenstates between x prime and x prime plus dx prime. Since the measurement outcome in quantum mechanics cannot be predicted, one actually works with the expectation value, and this is the averaged measurement result that one expects, and this is known as expectation value. So this is something that can be predicted. Here we cannot predict the particular measurement outcome. So the expectation value of an operator, that is represented like this and is given by this definition, same as in classical probability theory. That is just the parameter times its probability density times dx. This probability density within quantum mechanics is given like psi x mod square, and the psi x mod square is basically psi x psi star x. So we write this as psi x psi star x. This then we can write this we see this x outside, that's more like an eigenvalue equation, so we can write it as this. We are just rewriting it as this. Now we see that this x this is equal to 1. This is the completeness relation of a basis, and with that we could just write this x, that is the expectation value, as a psi x operator psi. So that is the expectation value of this position operator, but this is the same thing as we get for any operator. So any operator we have in quantum mechanics, this quantity is the expectation value of that operator. This is the averaged value, average measurement value that we will obtain of that particular physical variable. The other concept is the uncertainty in quantum mechanics. And this is defined, so we can not only calculate the expectation value of x, but we can also calculate the expectation value of the second moment, and the uncertainty is defined like this, which is the uncertainty, the expectation value of the second moment minus square of the expectation value of the first and the square root of that. So that is defined as the uncertainty in x. So if the system is in one of the eigenstate then the uncertainty is 0. For example, if we have the system in the momentum eigenket, and one example can be what's known as a plane wave. A plane wave is an example of a momentum eigenket with fixed momentum value p naught. For such a state, if we calculate the momentum, its expectation value is essentially p0, because every time we make the measurement we get the same result. And so the uncertainty in the measurement of p is actually 0. We can have another example. Let's say here this is the example of a position eigenket. Something that very closely resembles a position eigenket is a wave, a diffracting wave coming from a point, and then that point is x0. So for this state, if you measure the position, every time we make the measurement we always get the value x0. So the expectation value of position is x0, but the uncertainty in the measurement is 0. So these are the two different examples of a state of a system being in one of its eigenstate, and for that the corresponding uncertainties are 0. But in general, the system is not in the eigenstate, and at that point the uncertainty of the physical variables are finite. So for example, if this is the wave function, this is the momentum basis wave function of a system coming out of a single slit that we actually saw. So this is the momentum basis wave function. and the corresponding position basis wave function is given by this. Now here we do see a range of momentum values that are possible. So the width of this function broadly then defines the uncertainty in the momentum measurement. Again, for this example, if we make the measurement of if we make the position measurement, we will find the particle to be anywhere between minus a and a, and hence the delta x, that is this width, can be taken as the uncertainty in the measurement of x, because if you make a x measurement or the position measurement, it is likely that we find the particle anywhere between minus a and a. Here in fact is the equally likely to be anywhere from minus a to a, and here we have a distribution as to where we would actually find the particle. So in any case, the width of the such distribution we take as the uncertainty, and the exact definition is this. Okay, now we come to the concept of Heisenberg uncertainty relation. So we know that for a pair of conjugate variables such as position momentum, for example, position basis we represent in terms of this momentum basis vector, and for such pair of conjugate variables we have, for example, for position momentum we have that the commutation of x and p, that's not equal to 0. And for such pair of conjugate variables, the uncertainties of measurements are related like this, that is delta x, delta p has to be greater than h bar by 2. This is known as the position momentum Heisenberg uncertainty relation. So this basically says that both the position and momentum cannot be measured with infinite accuracy simultaneously. So if we can measure the momentum position very accurately, then of course we can't measure the momentum very accurately. Of course one can have infinitely accurate measurement of position. For example, if something is in position eigenket, then of course we can measure the position with infinite accuracy exactly. But for that position eigenket, the momentum measurement will be completely uncertain. So in general, position measurement and momentum measurement, they are position uncertainty and momentum uncertainty, they are related by this inequality, and this is known as Heisenberg uncertainty relation. We have similar Heisenberg uncertainty relation in other pair of conjugate variables as well. For example, time or arrival time and the energy, they also form an uncertainty relation, and which is called the time energy Heisenberg uncertainty relation. We can also have very similar uncertainty relation with angle and orbital angular momentum. So in general, whenever there is a pair of conjugate variables connected such that their commutation is not equal to 0, then we have a corresponding uncertainty relation, which essentially says that both those variables cannot be measured simultaneously with infinite accuracy. Okay, so these are the basic concepts of quantum mechanics. One final concept that now we want to discuss is that of field quantization. Of course, this is like a course in itself. Some of you might have done it, but I'll just do a very quick review of the field quantization. So within quantum mechanics, when dealing with particles of mass m, when we deal massive particles, we write the Hamiltonian as p square over 2m plus some potential. And here for the massive particle, we actually then work with position and momentum operators x and p, and in fact most of the concept that we have just reviewed here, we have done it in terms of position and momentum operator. So when we deal with massive particle, we work with position and momentum operators. However, when we deal with fields, we don't work with position and momentum operators. The Hamiltonian of a free electromagnetic field is given like this. So this is just a classical electromagnetic energy, which is what becomes the Hamiltonian when we quantize the field. So that is the form of the Hamiltonian that is given in terms of electric and magnetic field. We see that here the time and position, these act just as a parameter. So when dealing with electromagnetic field, we actually work with field operators E and B, and not with x and p. And all the dynamical variables corresponding to the field are expressed in terms of the E and B operators. The position and momentum, they simply act as parameters when we handle fields within quantum mechanics. The Hamiltonian, the corresponding to the quantized field, is actually written in terms of creation and annihilation operators. So this Hamiltonian is written like this, where we introduce this A dagger A. This is the creation operator, and this is the annihilation operator. This is the this annihilates a photon, and this creates a photon, which we will get to in a minute. This is called as creation operator. This is called as the annihilation operator, and the point is that this energy of the electromagnetic field can be written, the Hamiltonian can be written in this form. This has the implication that this says that in a given electromagnetic mode labeled by this wave vector k and polarization s, the amount of energy can only be increased in steps of h bar omega, and this h bar omega is then called one quantum of energy. Now, in terms of, and again here I am assuming that most people have done this field quantization. I am just kind of reviewing. For those who have not done it, they can actually follow Optical Coherence and Quantum Optics book of Mandel and Wolf. Now, in terms of this A dagger and A, the electric field operators, the electric field operator can be represented like this. Of course, the magnetic field operator will have very similar representation. So, essentially when working with electromagnetic field, we write the Hamiltonian in terms of electric and magnetic field, and that electromagnetic field we represent in terms of this creation and annihilation operator, because working with this creation and annihilation operator makes the maths much simpler compared to when we work with the E and B fields directly. Okay, so the state of the field, the state of the electromagnetic field, that is represented in terms of the quantum of energy, and there can be various ways of kind of representing it. For example, if we this ket vac or ket 0, this is just a vacuum state. This is a state with no quantum of energy. In fact, these states also have this half h bar omega energy associated with them. For example, there is a half here, but typically when we write the vacuum state, we don't write that half. So there is no quantum of energy associated with this. When we write a state like W or 1W, this is the state of one photon with energy h bar omega. If we write it like this is a state of one photon with wave vector q. These are just the different labelings that we have. This we can write the state of one photon with orbital angular momentum LH bar. This h or 1 over 1 and then sub h, this is a state of one photon with horizontal polarization. If we can also write the multiple photons, for example, this WSWI, this represents a 2 photon state with first photon having energy h bar omega s and the second photon having energy h bar omega I. This represents a 2 photon state with first photon being horizontally polarized and second photon being vertically polarized. So these are just the notation. Similarly, we can also have this for the state representation, and this essentially is an n photon state where each photon has energy h bar omega. So that's how we represent the state of the electromagnetic field, and the basis that we are using to represent the field here is the photon number basis, that is how many quantum of energy. So that's a photon number basis. This is not position or momentum basis, this is the photon number basis. And the action of the creation and annihilation operator on the photon number basis is as follows. So if it's annihilation operator, for example, the annihilation operator at frequency omega, if that acts on a state with n photons at frequency omega, then that gives a state with n minus 1 photon with frequency omega. Of course, this root n that comes out. If it acts on a vacuum state, then it actually gives 0. On the other hand, the creation operator, when it acts on a vacuum state, it creates a photon. So the state then is given by 1. Of course, this omega is just the frequency labeling. If this acts on a state with n photons, then it generates state with n plus 1 photon. So that's why this is called a creation operator. So this is in very brief how we handle electromagnetic field within field quantization and so on. So I will stop here, and thank you.